What up, Kyle?
Yeah, nice hat.
You got us? Let me get a second here.
All right.
You're on the screen. I think the audio should go through that, right? Hey, Kyle, talk. Will you talk?
Can you hear me?
Why, fuck, man. All I can hear is through this thing. 1 second.
Yeah, take your time.
Might have to do that. I thought that would go through that. All right. For some reason, you're not going through the speakers. I'm gonna hold on. All right. You there, Kyle?
Yeah. How about now?
Yeah, for some reason you're not going through the roof speakers, but here, talk a little bit, see if people can hear you.
I can talk loud too.
That you get that work for you guys? Yeah. Okay. No, I think it works, Kyle. So I'm gonna give you a quick rundown. So I don't know how much you're gonna introduce yourself, Kyle, or not, but do you see the class? You should be able to see the class.
Yeah, I see your class.
They're not very good looking, but they're there. So there's about 18 of them, right? And so Kyle was a student of mine probably 10-ish years ago, right? Everything he learned from me. I think that right, Kyle?
Yeah.
Yeah, he doesn't look very smart, but he's actually very smart. He's surprisingly smart. But you graduated your undergrad degree. You then worked for a concrete company, Baker Concrete, and then you did a lot of the construction on the post-tension designs or post-tension area. And then you came back to school and got your master's, and then went to Denver and did a lot of design associated with this. And then now you own your own business in with this KSB. He owns his own business in Missoula, and keep going with this design stuff. I don't know if I missed anything there, Kyle, but
Yeah, no, that was perfect. So yeah, as Barry said, did undergrad and grad at MSU. I took this exact class, taught this class as I was taking it.
that's true. Corrected me all the time.
Yeah. But besides that, though, yeah, Barry taught me everything I know. He'll tell you I'm really good at spelling. I learned it all from Barry. Smartest thing I ever did was marry somebody who's not an engineer and made real money. So yeah, there's really no money in design engineering. I'll tell you guys that right now. Not to break your spirits here, but I was on the construction side. I did the design side, and then I moved into a company where we did pre-engineered light gauge buildings and large buildings, 500,000, million square foot buildings on there. And I moved into an executive with that company. That company was private equity backed. And long story short, that company got sold off to the Saudis. We had an office over in Krakow, Poland, and I oversaw two. And when we shut down that company, I started up my own company, and I flew over to Poland. I have a small company in Poland, and we do some design in Poland, but they're also more my back of the house supports. They do a lot of engineering, a lot of modeling, drafting for me, and they're awesome. I get better product out of them than I do most of the U.S. engineers that work with me or for me, and they cost me half the amount. But we're licensed in 24 states. We're doing stuff all over the place, from California to Georgia to DC. A lot of weird miscellaneous things. But one of the topics that I specialize in is post-tension concrete. And so over the last probably 8 years or whatever it's been, Barry, I've taught a couple week segment of this course where you dive into PT design. So for you guys that are getting into bridges and ASHTOs, this will be a little less relevant, but there are some concepts if you're doing unbonded post-tensioning in the bridge world that still apply. If you're doing just pre-stressed girders like you see in Montana, then it's essentially what you've learned so far. When you start getting into bigger bridges, box girders, those type of bridge elements, there's a lot of unbonded post tensioning or bonded post tensioning in those. So the concepts that we'll talk about with balanced loading and kind of all that apply. But to start, we're going to just get into two-way slabs, which is kind of like what you're seeing up on the picture right now, where two-way slabs are what you will most likely come across, maybe some one-way parking garages throughout your career if you're doing buildings. And so when we talk about two-way slabs, that's what you're staring at right here. This is what a finished deck looks like for a two-way parking slab with unbonded post tension. And you can see there's really not much rebar in it at all. It's a bunch of red cables you see going back and forth, and then Smurf tube, which is just electrical conduit that's running through there. So as we talk about the type of buildings that we're going to do post tensioning in, a lot of them are residential in nature, high rise, above 4 or 5 stories. And that's because 5 stories or less, you can be a wood building, right? You see that all throughout Montana. Once you get above 5 stories, you can no longer be wood unless you go to IBC just recently allowed you to do mass timber above 5, but because of the combustibility reasons. So anything above 5 stories, you have to be a non-combustible structure, meaning you have to be concrete or steel. And so when we look at the building that I'm showing up on the screen right now, that's a 33-story building down in Denver. And it's one of the buildings we did quite a few years ago. And the choices were do it out of steel, do it out of traditional concrete, or do it out of post-tension concrete. So when I say traditional, I just mean mild beams and slab. Well, with post-tensioning, one of the benefits is you can use a really thin slab. So with that thin slab, what we can do, let me see if I can't get the pen to work. All right. With that thin slab, we had a height limit on this building of 300 feet. And that had to do with zoning. And what we were able to do was we were able to make this 33 stories tall. And with the post-tensioning, the post-tension slabs are only 8 inches thick. If we were looking at steel, we probably would have been about 2 feet thick of structure. If we were looking at traditional concrete, we maybe around 18 inches. So we saved at least a foot per floor going all the way up. And so because of that, we were able to add an additional 3 stories to the top of the building within our 300-foot limit that we had, which was more units that the developer was able to put in, meaning his pro forma or his cost analysis made the project more feasible. And really that additional 3 stories was what made the project go versus not go on there. So one of the benefits of post-tensioning is the reduced overall height that you have with the building, where you're saving, at least a foot per floor going up. And when on these tall buildings, that really starts to add up. Another benefit out there is the weight. So because we have less slab thickness, right, we're going to have less weight, meaning obviously less foundations, which is a big impact on your foundations, especially when you're talking a tall building like this. Another is this was a conference center down below, and then it was a hotel and apartment up above. And the columns that you can see in here on the left-hand side, those didn't necessarily stack out with the layout that you're going to have down in the conference. So after we got down 30 stories right here, we had to do giant transfer beams to get over the convention space. And Barry, this is where years ago when you guys were down in Denver for whatever conference you were down there with Clint and everybody, this was that building right there. So you need that big open space there. And with doing post-tensioning, that reduced weight allowed you to do a smaller transfer girder that was holding up, 30 stories up above it. The other thing it did is it reduces your seismic mass. And if you have a reduced seismic mass, you obviously have reduced seismic forces on here. Being in Denver is wind controlled in the long direction, the left-right direction, but in the short direction, it was seismic controlled in their design. So it helped out quite a bit with a lot of those force transfers with the seismic design. So not only is it saving building height, but it's also saving seismic mass, foundations, those elements there. As we go on, here's another building in Denver. And this particular one, they were fixed on the number of stories they had. Just coincidentally, it was another 30-story tower up here. And with doing post-tensioning, being able to save that foot, per floor, there's over 400 feet of exterior lineal footage of skin around this building, right? And then times 30 feet of floor that we were able to save, 1 foot per level, times it was almost $40 a square foot for your exterior skin on there. And then once you install your labor and all that stuff, we were able to save $500,000 on the project right there, just on exterior skin, and not even having to do things like, you have every foot you go up, that's additional foot of plumbing that runs vertically on your chases, HVAC that runs vertically going all the way up. Again, more wind, seismic, so bigger core walls, shear walls going down the building, bigger foundations, all those things. So it's a domino effect of these savings. And then with these post-tension slabs, there's so little material that goes in there that you're able to pour a floor a week if you get your schedule right. So here's another tall tower, and then you can get up here, you can see they just, this is all the formwork for the level going up. They were able to put in all the reinforcing, pour the concrete, stress the post-tension tendons, drop the tables, set them up on the next floor, and repeat that cycle and do that once a week, which is a crazy fast schedule on there. And one of the tricks of doing that is after you pour your slab, then that same day, as soon as you're walking on that concrete after you burn the finish, you're over here pouring your columns on top of it. But the reason why you can go so fast is from the reinforcing standpoint, you only need about a day and a half to 2 days to get your reinforcing in. You can see there's really no rebar in the slab. There's only a little bit of rebar over your column heads right here. You can see the column there. And the rest of the rebar here, this is just to support the PT tendons at their elevation. So it's just support steel. You might have a little bit of localized reinforcing at some blockouts. This was a shear wall right here going up. So yeah, we're gonna have a little bit of steel to drag some of that load in for our wind or seismic into the core wall there, but really not much. So you're able to lay this out pretty fast, accelerate those schedules. That acceleration of construction schedule that you see with post-tensioning, every week that you're not on the job and they're able to do it is a week less that they have to pay for the job trailers, the superintendents. And then, that term's called general conditions that the contractors will use. And those general conditions costs are extremely high. There's builder's risk insurance. There's a lot of things that go into every week that you're live on that project. So if you can save a month or two on your schedule, on your critical path, just by choosing a building system, that's another big domino effect of using post-tensioning out there. Other areas that we've seen it is, here is another building we did where they owned the airspace, but they didn't own the ground space. So we had to do a 180-foot long transfer girder right here that supported the rest of the building sitting on top of it. Down below, this was owned by the city. This was a bus lane that came through here. They were able to get an easement and put a single column right there, but they had to go up 40 feet before they were allowed to do a building. So it's kind of a weird concept to think about, owning the airspace but not owning the real estate down on the physical ground itself. But to do that, we did this 180-foot girder, supported this entire side of the building right here, right? And we were able to do that with post-tension because we were using post-tensioning in the drape, in the post-tensioning, it's kind of smiley face drape through here to pick up 80% of the building weight on this face right there. And on the right hand side, you can kind of see a picture of, this was as we were going up, kind of getting up out of the ground. What we did was we slipped the concrete cores going all the way up, because it was a steel office building. Once you got up above the parking levels up here, it was steel from here on up. And so you slip the concrete cores up to get them out of the critical path. You had, it was parking garage, it was a one-way post-tension slab. And then once you got up above, this was where that big transfer girder came across this bus lane that's over here on there. So that's just another use of it. Use that you're seeing in Bozeman or throughout Montana more and more is these podium structures. And a podium structure, all you're doing is you're transferring out 4 or 5 stories of wood up above traditionally. And that's usually because your bottom level, 1, it's too tall to do wood. 2, it's your bearing walls don't lay out with your architectural program down below. It's open amenity space. It's where you walk into the hotel. You don't want all these walls going in there. And so you do a podium slab, which is essentially a 2-way transfer beam, right? It's a 2-way flat plate transfer beam that you're staring at. This particular one's in Atlanta, and we did 12 stories of light gauge steel right here. So we had a 12-story building on top of a single-story podium. Here's a picture of that podium with all the reinforcing. There's a lot of stuff in there, but this podium was only 24 inches thick, so it was only 2 feet thick, and it was holding up 12 stories of building up above it. The podiums you'll see with wood, they're usually 12 to 14 inches thick, somewhere in there. And the reason why they can be so thin, again, is you're using this post tensioning to try and pick up that load, and you're also putting the pre-compression into the slab itself. So those are the applications of, why to use post tensioning. And post tensioning is not new. It's been around since it first started coming out in the 60s and the 70s. They did a bunch of testing on it. So it's been well established for over 50 years and used throughout the country. It's not this new concept. It's new to being taught at the university level, but it's definitely not new to the industry out there, aside from Montana. But the rest of the world knows of post tensioning, and they use post tensioning pretty heavily.
Cal, really quick, I guess I forgot to mention that you're the chair of the education committee for PTI. Is that right?
Yeah. So I sit on three or four committees for the Post Tensioning Institute. I lead the education committee, which we do a monthly webinar, and really one of our things is just to get information out to the world out there. Then I sit on the main design committee, voting member on that one. That's really, we take the stuff and we go back to ACI 318 and 320 now with recommended code, building code changes on there. And then say another one for parking structures and another one for barrier cables within the Post Tensioning Institute. It's one of those things, you want to put so much effort in your career back into professional organizations, right? PTI, ACI, AISC, whatever one you love to do. But that's not where your money is going to come from, right? And I watch all these engineers put hours and hours towards these organizations, but they don't put any hours towards business development or chasing new work or following the dollar symbol. And I think it's important to balance both those as you guys start, looking at extracurricular things in engineering. Put a lot of time towards giving back to professional organization, and definitely don't just go join a committee and not do anything for the committee. Be an active member of society there, but then also put a lot of time towards. At the end of the day, we're in this to make a dollar, right? So put time towards business development, being more efficient as an engineer, as a company. Focus, almost put more time towards that as a little side note for you guys.
One more comment on that. When you become a professional engineer, you have to do continuing education credits along the way, and then participating in these conferences does that. It counts as continuing education.
You can sit on my free monthly webinar and get free continuing education credit too.
Yeah. Hey, Kyle, we had a student ask about, is there a link to where all those webinars are at, or are those?
Yeah. Yep. I can send that out to the class.
I can come up with it too. So.
Yep. Because they're recorded, and for you guys, if you're not licensed, you don't need them yet, so you can just watch them, get your jollies out of it. But for ones that when you do need that, you watch it, you take a little quiz at the end, and then you get your continuing education credit through there. All right, so we talked about where do you see post-tension buildings. We looked at a bunch of pretty pictures. We talked about you really see it traditionally over 5 stories because you just can't compete with wood. Wood's going to be $25 a square foot to build, plus minus, depending on where you are in the world. Concrete's going to be $40 a square foot to $50 a square foot. So, and that's post-tension concrete. Steel's going to be even more expensive if you're in that doing a similar type of building. So really, when you're looking at an apartment building, concrete's going to behave way better, but it's just not going to cost performance. You're not going to get your performance to work for apartments or condos with 5 stories or less out concrete. It's going to be a challenge. That's why everybody always goes to wood. When you look at podiums, the reason why they want to do 5 stories over 1, and now the building code allows you to do 5 stories over 2, so 7 total stories. You want to take advantage of the efficiencies of those upper 5 levels of the $25 a square foot, and then do the concrete down at the lower levels while also opening up that floor plan with that podium. Parking garages, post tensioning is great just because of the durability that comes along with it. Office towers, some areas in the US like DC, Atlanta, those areas, they do use post tensioning in office towers a lot. Other areas like Denver, they're hesitant because a lot of office buildings, you're always pulling out beams to put in stairs, and they're a little hesitant on that, but we've recently come across a way to bypass that. Structural slab on grades on expansive soil. So when you have just a slab on ground, a mat slab, and you're on clay soil, you can use post tensioning to kind of overcome those effects of either the soil swelling or shrinking and the slab either cantilevering or trying to bow upwards, you use post tensioning to overcome those effects. Sky transfer mats, you know, those big buildings that I was showing you where transferring out 30 stories up above, sometimes you just do a really deep slab that's 8, 10 feet thick, and you can transfer out an entire skyscraper above it, and then you can have down on the first level that more conference space down in there. So, so those are a lot of areas where you see post tension being used often. The benefits are you span the depth up to 45. When you're with steel, you're 20, low 20s. Same with concrete in there. You know, my general rule of thumb on sizing a steel beam is take the span in feet, convert it to inches, divide by 2. That's about the depth that you need for vibration issues. So if you got a 40-foot span, you're really going to be putting a W21 in there. And when you look at post tensioning, you can be doing a 40-foot span with a 9 to 10 inch thick slab. So it's a gross cross section all the way through. So you're not dealing with crack cross sections when you're looking at long-term deflections. You know, reduced amount of concrete material, which is a high cost these days. Structure height, we went through that. Foundation, seismic mass, we kind of went through all that stuff. So now we're going to dive into, you know, what even makes up these post-tensioning systems? What do they look like? And we're going to start at the tendon level. So when we say tendon, the definition of a tendon is everything that's put together, the grease, the sheathing, everything we're going to talk about. Strands is just the steel in there. And tendons, sometimes when you're doing bonded, can be multiple strands that run through there, multiple groups of steel. In our case, a tendon, because it's unbonded, is only going to be a single piece of element that's running through your slab on there. So that single piece of element, it's going to be a 7-strand cable. And it's going to have a center strand in the middle of it. That center strand is the king strand. And then so it kind of runs right down the gut. And then your other 6 spiral around there. You have that ultimate capacity of 270 KSI on the steel. It's very high strength steel. It's also pretty brittle steel. When you go from yield to rupture, there's not a lot of room between those two compared to more like a grade 60 or any of those others if you look at those deflection curves on there. It's unbonded, meaning it's never going to bond with the concrete. So to not bond with the concrete, there's plastic sheathing, and that's what we're staring at, this kind of baby blue looking thing over the outside. And then there's grease that's coating all this stuff in there. And that grease is going to do a couple things. One, it adds corrosion resistance to the strand. 2, it allows it to slide smoother throughout that extruded plastic sheathing. That plastic sheathing, it's not just like a hose sheathing. It's actually extruded onto there, so it's got the same exact shape of the strands as it pulls through on there. And then this system is going to remain unbonded forever. So if you were to ever drill into it, the thing would pop and you'd lose all your tendon force because there's nothing bonding it to the concrete. There's no development length. There's no force transfer length associated with it because it's unbonded all the way through on there. The anchors, when you look at the end of the anchors, if it's an elevated post tensioning, it has to be encapsulated. So you can see the red, that's just it's hot dipped in plastic, and that's just corrosion protection, but it's really a steel anchor. They're a little wider, like 2.5 inches by about 5 and some change inches in each direction. And that's going to transfer all your force into your slab at the end. Whereas when you guys are looking at the bridge girders, right, that force is being transferred just through a bond, through some length of transfer. It's just through a bond between the tendon itself and the concrete. Well, now we don't have that bond, so we have to have a way to get that pre-compression to the slab. That's going to go through one of these anchors that you're looking at. And the anchors, if we were taking a step further, I just threw in these 2 pictures because I realized I didn't actually have wedges shown in there. You're going to have these 2 little wedges, and you can see them here, and you can see these little tiny divots in these wedges there. Those little divots or teeth, they're going to bite into the tendon. So you're going to pull the tendon, you're going to release it. These wedges, they're not the exact shape of your cone. They're on purpose, but they're close. They're going to suck into this cone shape as that strand tries to pull back, and they're going to kind of act like a Chinese finger trap on one side. It's not going to let these teeth are going to grab that strand. It's not going to let those teeth, it's not going to let that strand slip. Then these wedges are going to pull into this cone shape that we're looking at right here. You can kind of see that cone shape right there. And that's going to be how we actually, then they're going to crack because it's not the same shape like that. that's how you're actually going to transfer the force from the strands itself into the anchor on there. And that force, when you stress them to about 33,000 pounds. You release it, usually drops right around to 29,000 pounds with some immediate losses of these wedges seating into the anchor here, and the slab, the elastic shortening of the slab just from the P over A in there. You're going to lose some of that. You're also going to lose a little more from friction. We're going to talk about that here in a bit. But so that's how we're going to transfer the force in. Now, again, it's got to be encapsulated, meaning it has to be waterproof. So at the end, there's a little plastic sheathing cover right here in this really blurry picture that covers the end for waterproofing. We already talked about the extruded sheathing that's on there. And then you have what's called a grease cap, but it's just a plastic cap that screws into the end of this thing after you cut your tendon tails. Now you have a waterproof system in there. And so that's what your anchorage zone looks like with these unbonded tendons. So if you were to look at a tendon in the field, you're going to see the anchors, you're going to see the sheathing on there. You're only going to see exposed steel at the very ends of it. So let's go look at what it's going to look like actually on the deck itself. You're going to have two different sides of the anchor. You're going to have what's called a dead end, and you're going to have a live end. A dead end is a non-stressing end, so we're not going to be stressing those tendons on the dead end side, right? A live end is the side we're going to be stressing on. So here's a picture of the tendons. They're in the edge form. This is your edge form right here. So your concrete's going to pour up against this. You're going to pull this thing off, and you're going to be left with these anchors that are embedded into the concrete with no access to them. You can't see them after you pour the concrete. You typically hold these anchors about 2.5 inches-ish off the edge of your concrete slab. This looks like a thicker slab. This looks like it was a podium slab, so it's probably a, I don't know, 14-inch deep slab on there. And you're going to have these dead end anchors. So they're just the true anchor on the far end. You're not pulling any tendons. These anchors are actually stressed onto the tendons at the factory. They do a thing called back stressing to make sure those wedges we were just talking about can never come loose. And then you can see here's the grease cap that's on the very end to make it waterproof. Here's that other cap that I was talking about right here to make the entire system a waterproof system on that dead end. So then on the other end is the live end that you're going to be stressing from, right? So that live end, you can see the edge form right here. You have these little pocket formers right here, and they're going to form a little block out into the concrete slab. That pocket former, when you pull the edge form, that's going to leave you a little gap that's going to let you get into the edge of the anchor to be able to stress those tendons. And this is the side that you're going to, the sequence of events is you're going to rip this edge form off. You're going to pull these pocket formers off. You're going to put those wedges in here and here, like we were talking about. You're going to pull on that tendon to 33,000 pounds. You're going to release that tendon, and the elongation you're going to get on this tendon, it's going to be 8 inches, 12 inches. It's going to be a pretty big elongation. It's just a basic PL over AE elongation type of a calculation on there. It's going to try and suck back in as soon as you release it, just like a giant rubber band, but those two wedges are going to capture it, not let it suck back in. It's going to transfer that 33,000 pounds into this little 2.5 inch by 5 inch anchorage zone. And then it's going to put into the slab. Now our slab's in pre-compression. We have that P over A of 33,000 pounds minus those initial losses. So 29,000 pounds right at the beginning of slab, right at slab stressing. Right at that point, we haven't gone through our long-term losses yet.
Is that so? So you guys always use the same standard size? It's because you're talking about 33 kips, but that's for a certain size, right? What's this?
So yeah, great question. So that's for a 1/2 inch diameter, and that's the most common size to use for unbonded post tension is 1/2 inch diameter strand out there. And then with the sheathing, that adds another 1/8 of an inch to it, so it's a 5/8 of an inch. So you always use number 5 rebar with it too, because that matches your thickness of your PT strands on there. All right, so here's what those tails are going to look like. Point to go. Here it is. This has the formwork stripped out below, and technically you're supposed to cut these tails like the very next day before you even strip formwork, but for a certain reason we didn't do it. We fell behind, and you can see the little pocket right here. That was the block out that I was telling you about that this little pocket former held, and that now we're able to get into there and stress with our machine. We're able to get on these things, pull them this way with that 33,000 pounds that we were talking about. And then when we're done, when you come back in after it's stressed, you come back, you cut these tendon tails, and then you put that grease cap on there, and then you grout that hole back in. So you can see down below, you can just slightly see these lighter color areas. That's where you've grouted back the hole where you access those PT tendons on there. You can see we grouted back a couple on here already. We were kind of in the process. We're coming through and starting to cut these tails. There's two ways to cut it. There's a giant shear machine that they make that you can just shear them, or you just get in there with a torch and you just torch the end of those tendons off on there. All right, so now we have a good idea of what a tendon looks like. We talked about it's unbonded, it never bonds with the concrete. You have these anchors at the end, you have a dead end, a live end, and you stress the live end, you cut it afterwards. We now know how, we even get the force into the slab, the basics of it, right? So now we're going to dive into talking about what these layouts look like in the field. And the first one is, you're going to hear this called a lot. It's a banded tendon distribution. So in one direction over your column lines, you're going to band all your tendons together. And it almost looks like a beam, but it's not. All you're doing is you're just taking your tendons, you're banding them together right over the column heads. And they're spaced on about 12-inch spacing. Right there, from center line to center line. Each tendon group usually has a max of about 4 tendons, 5 at absolute max. Can be as low as 1. And this is a number of force that's figured out. We're going to get into it later on, but you as an engineer, you're going to figure out how much force, and you're really going to figure out approximately the number of tendons. The tendon supplier is going to do the friction loss calcs and verify it, even though this tendon group has 25 tendons or however many number it has on there. But the big thing to remember is your banded tendon line. It's the first one that goes in, and it's banded just like the word along a column line. Typically, you do it in your longest direction. Then what you're going to do is you're going to come in, you're going to do Yep.
Why are we banding them?
Give me one more slide and we'll get into that. Yeah. So the other direction, you're going to have a uniform group, and this uniform group is spaced at either 8 times your slab thickness or 5 feet, whichever is, that's a 5. 5 feet, whichever is most restrictive, right? So most of the times it's 5 feet on there. You can see this is the podium slab. They've already started forming the wood up above. The framer was right on us as we were pouring, and we're going as fast as we can. You can see the banded tendons running left to right, and then you can see these uniform tendons running into the page. The other thing that we can start to notice on this one especially is the drape, right? So you can see we have positive drape in the middle, meaning we have smiley face. We're picking up. And that's in our positive flexure region. So we're picking up in our positive flexure region. And then in our negative flexure region along the column line, we're pushing down, right? So we're doing the opposite of what the slab's trying to do. Same thing with our banded lines. A big misconception when you look at this is this thing looks very much like a one-way slab, right? It looks like this is a beam line. It looks like this is your slab line, and you're pushing down on your beam, and this beam's picking up and bringing it to the columns. That's not how it's actually behaving. If you look at two-way bending, you have negative moment over your column line in this direction, right? So you're pushing down to counter that negative moment. You're not pushing down over this theoretical beam, even though it looks like that. And most engineers, when they get into PT design, that's the first thing they think of. It's the first thing when I was building, that's how I thought it was. It wasn't until I actually taught Barry's class that I realized it was different on there, but that's how this thing's laid out right there. You never want to have negative flexure, frowny face curvature in the middle of a positive region, because now you're just pushing down, right? Versus the same time, you never want to be picking up, picking up where you're supposed to be pushing down over the column heads on there. And we're going to go to the next slide and talk about what Barry was asking. Why do we band them together in one direction? So back in the 60s and early 70s, they did what was on the left-hand side here. It was called a basket weave distribution, which was very similar to if you're doing a two-way slab designed by Mild Steel, right? You can see right here a cluster of tighter spaced tendons over your more column region, your center region, and then you can see your middle region having less steel in there, and then clustered again, and you can see that in both directions. That was the layout. All they did was they mimicked how rebar was placed, and they mimicked where your max moments are going to be. Your max moments are on your column lines that they did when they first started doing post-tensioning design. Worked great from the concept of their proving post-tensioning in the late 60s, early 70s. The challenge was that basket weave of trying to install. Remember, what we showed in the previous slides was first you put down your banded tendons, then you put down your uniform tendons. It's a real simple installation. Well, this way is too much of a basket weave, and they're having a hell of a time in the field trying to put it together. So down at UT Austin in the 70s, they said, let's do a test and let's design it exactly the same, but take our tendons and band them together in one direction. The design's exactly the same. Nothing's changing our design analytically. All we're doing now, instead of having our tendons spread out and having a column strip, middle strip, is we're just going to say, hey, it's equivalent frame, and we're going to push it all together into one direction. And so now when we analyze slabs, we look at it as equivalent frame. So you're really looking at your trib width, and you're analyzing it based on, here's all the tendons. We don't care where it is within that width. It's just like a piece of rebar and a beam. You don't care where it is left to right. You just care where it is up and down. Now we're doing an equivalent frame. We're still going to do the equivalent frame in the other direction. And now we have a much easier way to do that. And this is the way that everybody does PT tendons since the mid 70s. And the basket weave, as soon as this was proven and code adopted, it went away. Recently, just this year, ACI has come out and said, now you can band them together in both directions. And this had to do with a lot of research that was done over the last 10, 15 years. When I was in grad school, my professional paper was on banding in both directions together. And I did a bunch of analytical research. We brought PTI. We then went to Virginia Tech and we did third scale testing on it. A lot of the members that sit on PTI, that design committee I'm on, they also sit on ACI 318. They got fed up with ACI 318 taking forever, so they started their own code called ACI 320 and got 318 to essentially say, okay, 320 is another way of going about doing it. It just came out this year. And in this year's code, it now says you can band tendons together in both directions. And the benefits of this are a couple. One is now in the future, if you want to go do a stair opening, look at this huge area that we can drill into without hitting a post-tension tendon. We can go retrofit a stair opening.
Is there mild steel in the middle of all that stuff, or is it just
very little? So it's 0.001%. It's equivalent to, for an 8-inch thick slab, it's equivalent to number 4s at 24 inches on center each way for bottom steel. You don't need it for any analytical purposes. The only reason we put it in there is we thought the only way we're going to get through ACI 318 was by having some magnitude of steel in there. And then we also said, you know, what happens if you potentially overloaded this area right here with a giant point load, way bigger than whatever the design load was, but you never know what the future is going to bring. And you could potentially have this like hybrid of a punching failure in here with no reinforcing, or you could have this like starts as a punching and then kind of mitigates out to a flexural failure in both directions. And you could potentially maybe someday get something through. It had to be extreme load, but so we put in there just to provide some sort of ductility for an extreme overload event on there. But we don't use it for any of the analytics for strength or service or anything.
So kind of that research that they did, they looked at like the shear leg effect, is that right? Because you're putting it very concentrated and it's kind of out to the unreinforced. So I'm assuming they getting stuff or
so the shear leg that Barry's talking about is, so when we look at this banded tendon thing, right? We have giant pre-compression here, same here, right? But there's a shear leg of that pre-compression getting out to the slab that looks kind of something like this. And so this area in here really has no P over A to it in that direction. In the opposite direction, we have so many tendons that shear lag's so small that you really don't notice it on there. But that shear lag's been present this whole time in one direction. There's never been any issues with it. So now you just have the shear lag in two directions. Some engineers have tried specking some rebar as like a little, kind of putting some rebar in here. It's added rebar, you don't need it, it confuses everybody. We've never had any cracking happen there, because remember, you also have pre-compression in this direction that's getting in there too. So you have some, just through strain compatibility and Poisson's ratio and everything, you still have some magnitude of force dumping in that direction anyways from your perpendicular pre-compression on there. So we talked about this a lot, and we were very careful when we did the test to do the test without that steel in there, so that nobody could come back and tell us, well, the testing you did had it in there and you still need it, because nobody at PTI really likes that steel in there. So when we talk for the rest of the presentation, we're going to really be talking about designing banded uniform groups and that layout, although the design's not any different. The only difference is, you know, if you figure out you need 20 tendons here, and in this direction you need 20 tendons, there'd just be 20 tendons divided by some, you know, 5-foot spacing, and that's how many tendons you have every 5 feet. So the design's not any different. You're doing equivalent frame, but the layouts and the pictures we're going to see moving forward, it has to do more with this traditional method on there. But do note, now, as of this year, it is code recognized, although local building departments have to adopt that code, and they're usually many years behind on adopting the code. So it'll probably still be a few more years till we see it again utilized a lot, but it is code adopted by ACI 318 and the new ACI 320 code on there.
Has it been used yet, Cal? Have they done double banded yet? Anyway,
Not from the not how we're showing it, it hasn't, but it has been used just with more mild steel. There's been a couple slabs, and in one of the later lectures we'll show them where they've done it in New York City on a high rise, the big tall high rise. They did it, and then they did it down in Florida on a couple projects too. Because it wasn't code adopted yet, they had to put in the minimum area of steel that you would with a mild slab to get it through the building department. Okay, so we talked about the band tendons, the uniform tendons. There's a couple rules that you have to follow. One is inside your rebar cage, you always have to have 2 tendons here and here, right? And you can see these 2 tendons right there. That's integrity steel. In case there's ever an extreme event where the slab did punch through and collapse, those 2 tendons, believe it or not, are going to hold up the slab. And that was seen in Northridge. There was a lot of 2 tendons in between that were holding up the slab, even when all the reinforcement around the punching area completely crumbled from the shears and everything. You still have 2 tendons just barely holding up that slab. So that requirement still sits. You're supposed to have that in each direction. So one thing this picture is missing is there weren't 2 tendons going this way through the column head. However, there is a buyout if you can't get them in there where you can put a couple bottom bars in here as well. But that's a pretty big requirement that's required in there. The other is you can see there's just a little bit of mild steel over the top. If you do the strength level calcs, you don't need this steel. However, that steel is put in there for 2 reasons. One, it helps with crack control because you're getting a giant, if you look at your moment diagram, you're getting a giant spike in your negative moment. And so you're going to get some sort of localized crushing right here. The spike's probably not real. It's probably more rounded off, but in FEA, it's going to show you this spike. But you're going to get some little micro cracks there, even though it's an uncracked slab system. And it also provides some ductility in extreme event. Remember, in extreme lateral event, what's going to happen is you're going to see your negative moments reach their peaks much higher on a continuous member. And that's where you really need some ductility for some energy dissipation. Even though this isn't part of your main energy dissipation system, it's not your lateral, it's not your shear walls, your moment frames, whatever it is, it's still nice to have some sort of internal ductility to know that your slab can go along for the deformation capability of the inelastic drift, right? Because those inelastic drifts can become huge. And you want to make sure your slab can still go along for the ride. And that's a code requirement. So one of the things that makes you feel warm and fuzzy is having that little bit of ductility steel in there on that. Here's a beam, another area. So we were showing 2-way slabs. Here's a beam. This was a transfer beam. It was supporting, I forget how many stories, about quite a bit. And you can see all the tendons there, yellow. The color makes no difference. Different suppliers have different PT tendon colors. So for whatever reason, this installer bought tendons from 2 different suppliers. But you can see the yellow down there. And it's going through and it's picking up all the forces of this column in the middle about where this guy's vacuuming there's no column down below. It's this giant open 60-foot wide beam down below. So PT works great in transfer beams. I showed that big, tall 40-story Hyatt building where it's transferring out 30 stories above the 10-story convention area. That's another great area for post-tensioning. On there, areas that aren't great for post-tensioning are little tiny beams. You don't need them in these little tiny beams. Typically, you have a stiff element. There's no reason to try and pull them up. This engineer specified them. You can see just this cluster of just even trying to get the PT tendons into the beam with all the beam steel going on. You can see all the stirrups. They tried specing some unreasonable amount of stirrups because there's some junior engineer who didn't know what they were doing. And yeah, just total cluster. This ends up becoming issues. And I've got pictures of where this became big issues. And so when you have little beams, just leave the post-tensioning out of it. Only put it in there if you need the post-tensioning. Don't just put it in there just because you're doing it everywhere else on it. Here's a picture of the end of that transfer girder we were just looking at. So you can see all the anchors right here of all the PT tendons that are in there. So pretty big transfer girder. You can see those anchors. On the other side, we have the stress. That's the dead end, right? You don't see the tail sticking out. On the other side, we have the live end. That's where we're going to stress from on there. So great application for using it in a beam. Big transfer. We have lots of room. We have lots of real estate to put in the post-tension tendons. Again, another example on the right, terrible application of there. We're trying to die, I don't know, 20-something tendons into this beam. We can't even get it in because we have so much, we have these honking number 9 or 10 bars here and here. So we can't even get in at the right elevation. It's down lower. What ended up happening was because it was supposed to be up high in this plane. And what ended up happening because we couldn't get up in that elevation is we ended up with a frowny face curvature right here. Nothing to support it. We actually ended up blowing out all the concrete below this on this particular project there. Another issue where I have a lot of beef with this detail is if you have rebar in a beam, don't hook it down in when you have a slab right here. Take that rebar back into your slab because you're still going to have that negative moment right here just through stiffness. So you're going to form a crack on the top of your slab right there. So take that bar, make it continuous going through just in general when you have a slab element like that. So that's an example on the left, a great application of using it in beams. On the right, a terrible application of using it in beams there. We're gonna go over 3 more slides here, and then we'll call it because I know we're getting up against time. So the tendons, as they sweep, we talked about them vertically picking up because there's that curvature. Well, horizontally, it doesn't distinguish between vertical and horizontal curvature. You can see this curvature right here between the tendons. That drape, call that a drape right there, that's putting a huge horizontal force that way in the slab. That can roll out if you don't put in hairpins. Oops. If you don't put in hairpins or reinforce it. This is a block out for a mechanical shaft. Those tendons will just rip right into that block out. So you got to reinforce it properly when you have these type of sweeps. I'm giving you guys, at what type of sweep you need to start putting in these hairpins. These hairpins are just these U-bars right here. All they're doing is they're just dragging that load back into the concrete itself. We already talked about the minimum flexural steel at the top. There's some that we'll get into, ductility, crack control. You really don't need it for strength. Your PT tendons are usually more than enough on there. So we're going to not get any further into that particular one. In future conversations, we're going to talk about minimum area of steel if you exceed certain stress limits. At your column heads, they're thin slabs, right? So we're getting great span to depth ratios. What controls our design? It's going to be deflection. Well, we're going to overcome deflection by picking up 60 to 80% of our load. Then the next big thing is punching shear because it's so thin. So you put in these, they're called stud rails, but they're these little rails you see right here, back just like a stirrup for shear reinforcement. That's how you reinforce these slabs for punching shear, because that really becomes your controlling, one of your controlling design that's on there. So anyways, I think right here's a good stopping point. What we're going to talk about on Wednesdays, we're going to dive deeper into stressing and how the stressing sequence, the forces, pocket formers, edge forms, how you have to access the stressing like we're talking about now. And then from there, we'll start diving into kind of the fundamentals of restraint to shortening, other things you have to think about, and then we'll touch design. We'll start actually getting into the engineering side of it.
Cool. Thanks, Kyle. That's awesome, man. We'll see you on Wednesday, man.
All right. Awesome,
Yep.
guys. Thanks. Appreciate you being here. I'll talk to you on Wednesday.
Yep. Thanks, Kyle.